okay, let us start our today's lecture. So the last time it was sort of introduction, and today we are going to the subject proper. So as I said, the non-standard analysis deals with some extension of real numbers. But it is not enough. It turns out that we should create not just standard real numbers, but I would say standard mathematics. So we cannot make it do with less than to extend the whole mathematics. So what I start today is construction of some sort of models of mathematics. I mean the whole mathematics, all past, present and future. Yes, so you will see that everything which is even possible in this domain will be included in this model, and even much more. I would say a lot of nonsense will also be there. Yeah, so I start from, what is done, it is called superstructure. So what is a superstructure? Let us take some set S. To have something interesting, we have this S should be infinite, first of all, and then let me think that this set includes real numbers. So to start from. Yes, we can have a little less, say, start from just integer numbers, but let us take, it is convenient to have integer numbers and maybe some other objects. For example, if we think to work in geometry, just plain geometry, we can include there all points and all lines in there. Plane. So it is also possible, or maybe some other things. But in fact, we can take just integers or integers with something. So it is called a set containing real numbers and perhaps something more. And let us, for the future, denoted by S0. And now let us define the set S1. The set is defined as follows. It is S0 union with P of S0. What is P? It is the set of all subsets of S0. The set of all subsets of S0. So P of S0, say 2 to the power S0. S0. We can write in this way. Now let us define S2 equals S1 and P of S1, and so on. So we define as I plus 1 equals Si union P of S1. I are all natural numbers. And now let us define S cup equals union Si I is n. Union S0 because n starts from 1. So this is definition of superstructure. We will work with this superstructure. So my claim for now is that this superstructure contains all the objects of current and I think future mathematics. Okay. So how can we do it? Let us build it step by step. Suppose we have two elements of this superstructure. Here this superstructure has the following property, obvious property, that S0 is a subset of S1. So it is a growing sequence of sets by definition. The first object which we can look for where is the empty set. Yeah. So the basic set S0 is just the set of numbers, and we will think that all elements of S0 are not set, they are individuals. Yes, we don't regard elements of them. They are individual, and so empty set cannot be at the level 0. But empty set is a subset of any set, in particular of S0. So we can claim that empty set is element of S1. So we found already something. Now, suppose we have two elements of this superstructure. Suppose that A and B are elements of S. No, this means that, say, A in some Si, B in some Sj. There is an axiom in the set theory that if you have two elements of a set, any two sets or any two elements, we can form a pair. We can form a set such that its sole elements are A and B. So we can form a pair AB. So it is a set such that it contains A and B and nothing more. Now, in particular, if A equals B, then AB is a set which contains only one element A. I would say that it should be either proved or taken as axiom that for any given object like individual or set, there exists a set which contains this object as one single element. Yes, it's a matter of axiom. Why? Because we don't know what is a set. Yes, there is no definition of set. It cannot be reduced to anything more fundamental. So it is simply a name. And therefore, we can use our intuition, but know that it is shaky, especially if sets are very big. So we have this thing. Now, the next object which can be defined is the ordered pair. This is just a set, but the ordered pair is a pair when one element is called the first, other is the second. How it can be defined? So, ordered pair. It is denoted like this in the angle brackets, AB. So A is the first, B is the second. The definition is the following, or definition or construction. AB is by definition the following pair. Here we have the set with single element A, and here we have this set with two element B. So we can form the set with one element A, then we can form a set with two elements A and B, and so having these two objects, we can form also the set which contains just this and this. So elements of this set are two sets. What is one element with two elements. And now we have the following lemma. There is a lot of lemmas. In fact, it belongs to set theory, but it's important here, so I give it. If we have two pairs, A, B, is the same as A prime, B prime, then A equals B and A equals A prime and B equals B prime. So we have the following lemma. Now let me prove this lemma. So, so what does it mean? This pair AB equals A prime B prime. It means that this set AB equals the set A prime, B prime. So we have two sets and they are equal. So now, when are two sets equal? There is other axiom that two sets are equal to one another if they have the same elements. If every element of one set is the element of other and conversely. Yeah? So the set is defined by its elements. So here we have two sets. They are defined by these elements. And here we have the two possibilities. There are two possibilities. first possibility. A set of A equals set containing only A prime, and B is the set containing only AB equals A prime B prime. Yeah? So this element equals this element, and this element equals this element. So if A thing equal this set equals this set, so all elements of this set, each element of this set at the same time element of it. Here we have just one element here, so this element is equal to this. So A equals A prime. Now go to this. This A equal already is equal to A prime. So what remains is that B equal B prime. From this, B equal B prime. And the second possibility is that A equal A prime B prime, and A B equals A prime. Yeah? Because we know, we don't know which element here is the first, which is the second. So a priori we can have also this possibility. In this case, here we have just one element. Here we have no maximum two elements, but they cannot be different because the set of one element cannot be equal to the set with two elements. Yeah? So this means that A equals A prime equals B prime. And from here you have that this set of one element is equal to this set with two elements. And similarly we have that A prime equals A equals B. Now by transitivity, it is from this. By transitivity you have B equals A prime equals B prime. So both cases show that this lemma is true. So this means that we can liberally use this operation making ordered pair of any two objects. I say that objects can be both individuals from S0 or sets. Now, if you are able to produce ordered pairs, you can also produce ordered triples, quadruples, and so on. So we can define ABC, for example, equals by definition, here is AB, and here is C. Yeah? And similarly, going by induction, A1 AN equals by definition A1 AN minus 1 AN. So by induction we define these pairs, these ordered tuples for any finite number of, yes, please.
What do you mean by induction?
Excuse me?
What do you mean by induction?
I would say by recursion. Yes, so it is a recursion. There is an axiomatic scheme of recursion which makes it possible to define such objects. Yeah. Now it is interesting to see where do these objects live in our hierarchy of sets, in our superstructure. Yes? So suppose that A and A is in Si, B is in Sj. By the way, here was one not misunderstanding, by like psychological difficulty. We know that the set of subsets of any set is its cardinality is larger than for the set itself. Yeah. So in this hierarchy of sets, the cardinality monotonically grows, and starting from say S2, it becomes more than continuum, and then grows farther and farther. And so we can wonder if such large sets are of any use in analysis or in any concrete mathematics. Yeah? But we are not considering these so large sets. These sets are regarded not as big sets, but they are regarded as sets having a rich structure. Yes? So if the set is the set of sets, and each set is also the set of sets and so on, for n floors downstairs, then it has quite a rich structure and can hold a lot of interesting objects which are impossible to construct at the zero level. So here is the first step. Suppose we have A in Si and B in Sj, but because these sets are in part of one another, say if I less than j or less or equal than j, this means that A and B in Sj. Yeah? So we can consider them both at one level. Yeah, so then you can see that the set A with one element, it is a set with elements from Sj. Yes, just one element, but nonetheless it is a set of elements of it. So it belongs to Sj plus 1. And AB, element of Sj plus 1. And so, what is AB? Equals the set containing these two elements. So this and these elements are in Sj plus 1. Yeah? So it is a subset of Sj plus 1. So it is subset of Sj plus 1. If it is subset of Sj plus 1, then it is element of Sj plus 2. So AB, element of Sj plus 2. Yeah? Again, we are talking about very small set with quite a few elements, but we are climbing this ladder because they have the structure which is not quantitatively large, but qualitatively rich. Yeah? So therefore, we need quite a lot of these levels to hold interesting objects. Okay, now let us go further. What about these ordered sets of longer than 2 elements? So, A, B, C. It is A, B, and C. So suppose that A, B, C themselves are at the level as J. Yeah? Then this AB at the level as J plus 2, as we know already. Yeah. No, we can think that C is also an Sj plus 2. If it is at the level Sj, then even more it is at the Sj plus 2. And exactly by the previous, this means that ABC in Sj plus 4. Yeah. No, similarly, A1, AN in Sj plus 2n. So here are the ordered tuples. No, this is true for any basic set as 0. So here I did not use any structure. If we use this structure, no, okay, in a few minutes it can mean that we can see that much lower level. So it is in general. We can always raise the level, I think, because of this monotonic growth of the sets, but we can get much more economic. I will see how to do it. Now consider the following thing. Consider the set A a subset of Si and B subset of Sj. And now consider the following thing which we know already what it is. It is the Cartesian product of A and B. It is the set of all ordered parts A, B, such that A in the first set and B in the second set. Yeah? It is the Cartesian product, but now let us see, where does it sit? So each A, B is element of, I again assume that A and B are subsets of, say, Sj, where J is maximum of I and J. Yes? Then AB, element of Sj plus 2 for any A and B. Yes? if it is element of Sj plus 2, and here you have some set of these elements. So we have some subset of this. We have some set of S, a subset of Sj plus 2. Yes? This means that A times B is element of Sj plus 3. So the Cartesian product of A and B is 3 floors higher. Now, having this, we can define different objects related to Cartesian products. Namely, relation. What is relation? R, it is any subset of A times B. Any subset defines some relation. So where does it sit? So A times B itself is element of Si plus 3, J plus 3. So it is in fact some set of elements Sj plus 2. Yes? Subset is also a set in Sj plus 2. So this R element as Sj plus 3 as well. And if you have A in A capital, B in B capital, we can consider a situation where the pair AB belongs to this subset R. Yeah? Or sometimes we can write, it is the same, we write A, R, B. No example. A equals B equals R. Yeah? So consider R times R, and in this set we consider like this. Say xy such that x less than y. Yes? And it is natural to denote this relation by this sign, less inequality. And so we write like it is written here, A less than B is the same as AB element of R. We have already this notation. Yeah. No, it is one example of relation. And any order structure in any set is a relation, because order means that we say which element is smaller than which. So we have two elements, and sometimes we can compare, say that one is smaller than other. If it is the case, then you write A less than B. Or if you have it has some other meaning, this you can use some other symbol. Now we can consider also operation, another example of relation. To this end, let us consider, say, binary operation. So, operation which takes two elements and produces the third element. Yeah. So we have operation op. It is some operation. So to define it, we have to consider this Cartesian product. We have three sets, A, B, C, are sets in S. So three sets in this set, and consider Cartesian product A times B times C. It is the set of these triples. Set of ordered triples. Element from A, from B, and from C. And consider some set op, which is subset of A times B times C. Yeah. This is subset. And we say that C is by definition result of operation of AB if this triple ABC in this set op. No, we can substitute here any operation. No, for example, if AB and C are is the same real line, and op is the set of triple ABC such that C equals A plus B, for example. Yeah. Now, in this case, we denote, instead of this general operation, we write op equal plus. Yeah? And we write C equal plus of AB. No, it is not very convenient, so we can use just change notation and write it as A plus B. Now, similarly, we can define other operation, multiplication. Yes? But we can define much more. Okay, so having this, we can define the next thing. What is a function? called f, this time I denote a function by f, is a subset in A times B, yes, subset, such that if f is a function, if every time when, say, x, y in F, so x in A and y in B, and x and z in F, we have y equals z. Yeah? And in this case, we define y equals z equals f of x. Now x can be again ordered pair or ordered tuple of other objects. So it is a quite general notion. So this is a function. So the function has its domain of f equals the set of x in A such that there exists y in B such that x y in F. Yeah? So it is the set of x such that the function is defined. So domain of F is a subset of A, and F is defined on domain of F. So this is function. Now, still other general notion for function is restriction. Of a relation. Suppose we have a relation R in A times B. And we then consider some element x in A and define R, its restriction on x. And this is defined as follows. It is y in B if y is the unique element of B such that the pair xy element of F. In this case, it is y. And otherwise, it is an empty set. If I would say otherwise. So what means otherwise? Either we have no such y whatsoever, or we have multiple y's. In this case, we don't count them. So this object is has good, I would say, functorial properties. So it is one of very few notions which can be defined in such general setup. Now we have enough to see where are different interesting objects, more complicated objects. Where are they sitting in this ladder of space, of sets, SIs? So first of all, such interesting object as a group. Yes, just an abstract group. Where does it sit? First of all, we have to know to have the body of the group, the set of its elements. Let me denote the group by gamma, and this is by definition the following tuple. First, it is some set of elements. Then you have the group operation, which I denote by dot. And then we have the unit element in the group. So G, the group, is element of some SI. Yes, please.
Shouldn't we also have an inverse operator?
It can have members of different nature. It can be transformations, it can be matrices, and something unimaginable. Yeah? But in our universe, they are sitting at some ladder, at some level of this ladder. Yeah? So the set G is the level I. First of all, somewhere. Again, it does not say there's I that it is very big. Yes, it means that it has some structure. Yeah. Now, dot is a subset in this Cartesian product. G times G times G. Yeah, means here X, here Y, and here their product. Yes, and E element of G. So this subset G times G times G sits in S I plus 4. Yes? This an SI E element of G, so it is not in SI, E in SI minus 1, because it's merely an element of I. But we have to consider this triple. We have to first put them at the same level, and the only common level is SI plus 4. Yes, because we cannot reduce the level of this object. So we have to regard these elements which are lower level as elements of higher level, because we have this monotonic growth of levels. And so what does it mean that dot belongs? Z equals x dot y is the same of x, y, z belongs to this set dot. Yeah. Each of them belong to G. X, y, z belong to G. So they all these objects, G dot and E, all belong to S I plus 4. Now the triple of these objects, order triple, gamma G dot E belongs to S I plus 8, because it's order triple. Okay, so we somehow climbed the ladder, and we climbed the ladder because the complexity of our objects grows. Yeah? Now, similarly, if we have time, we can consider, no, I like this example. We can consider linear space. So what is a linear space? It has more structure. We have L belongs to some Si. It is the set of elements of this linear space. Again, as you told, each element can be, say, linear operator itself in some tricky spaces. So it cannot be too low in this ladder. So L in Si. Now we have two operations. We have one operation, addition of vectors. So we have two vectors, and after addition they are transformed in the third vector. So we have operation plus, which is subset of L times L times L. Yeah. So here we have F, here we have G, here we have H, and F, G, H belong to plus if F plus G equals H. Yeah. So correspondingly, we climb by four floors up here. Now we have other structure, multiplication by constant. Multiplication by constant, let me multiplication so what we take A times F equals G. So we have element, this set is a subset of R, it is here, times L times L. Now we have other operations here, namely scalar product, if we consider Euclidean space. Scalar product, how to denote it? No, let us denote it by dot this circle. Scalar product. So F scalar product with G equals say A. So it is in R, it is in L, it is in L. Yeah. So this set is subset of L times L times R. Yeah. So no, okay, we can add some other structure if we wish, but this is already a lot. So this means that linear space is the following tuple. It is L, then you have plus, you have multiplication by constant, and you have this scalar multiplication. Yes, and we can also easily count how many floors up it is in our ladder. So this is also good. And now you can believe me that the same way we can define Hilbert space, we can define the space L2, we can define in terms of these sets, we can define, say, Lie groups and anything else. Yeah. However, we are not able at this moment to say the say linear space. It should not only be some collection of elements and operations. So this operation should satisfy some conditions. Yes, so we have to define the way how to distinguish between, say, groups and non-groups, because we can define these elements in such a way, this operation in such a way that it does not satisfy, say, associativity. So we have to introduce some language. Yeah. So next step after here, one moment, if I can do it. Yes, I can a little bit. Is so we define, roughly speaking, where say at which level each mathematical object is. Now we have to define the tools how to say operate with this object, how to describe their properties. Yeah. For this purpose, we should describe a formal language. Denoted by L, just the language. So this language, the base of this language is some collection of symbols. The symbols are not elements of any material set, they are completely notations for something. Yes, so somewhere at the background we have our superstructure S. assumed fixed. In the language, we have symbols of L. These symbols fall into three groups. So the first group are, I would say, general logical symbols. It is the symbols equal, the symbol element, the symbol not, the symbol and, symbol that exists. Now we should use brackets just to have directions how to understand the formulas, and we have this important symbol restriction of something on something, and comma. We need only this. So it is the group 1. Yeah? So this symbol have no relation to any particular choice of S. They are general logical symbols. The second group is variables. So our language, what we write in this language, we write some texts. It is a sequence of symbols, and we consider only finite sequences. So the variables are just variable placeholders, so they have no the meaning of their own. They should be simply different. So we denote them, say, x, y, z, and so on, maybe with indices t, I, say u, j, k, and so on, maybe with some decorations. So we should have enough symbols. Enough means just a countable number of these symbols which have no the meaning of their own, just they are used like in the general mathematics to denote something which we put in their place when necessary. So these are variables. And the third group is constants. Now we can give A, B, and so on. Gamma, delta, say C, eta, and so on. So constants are in one correspondence with the elements of our superstructures. For any element of superstructure, there is its own constant here. Now you can imagine that the amount of these constants should be large, but in principle we should be able to denote each say element of superstructure at every level by its own name. So it's names of elements of superstructure. Names of elements of superstructure S. So they should be are in one-to-one correspondence with this S. So these are these are the elements. And now any text in our language is a finite sequence of symbols of one of these three groups. So this sequence or these texts or these strings are written according to some rules. So there is some syntaxes here. Yes, we cannot take arbitrary random sequence of these symbols. Usually it makes no sense. So first we should have syntaxes, and then after we study how to write syntactically correct sentences, we should semantics is the meaning, the rules how to give a meaning to each grammatically correct sentence. Yes? No, I think it is better to do it in the next lecture, to define the syntaxes and the semantics, so that we can write. So one of the first goals is to describe the object which I introduced. So how to describe a group, how to describe the set of all groups. By the way, it is not mistake. If you consider all the groups whatsoever, they don't form a set. It's too big. Yes, like the set of all sets. Last year I proved in my set theory course that any set can be given a structure of commutative group. Yes? So the number of group is not less than number of sets. Yes. Therefore, but here we consider just the groups which belong to our superstructure. This means that this group should be somewhere at some level in our superstructure. Yeah? And the set of elements of superstructure is the union of countable number of sets, which is also a set. Yes? So we can consider this set, and it is quite correct to talk about the set of all groups in our superstructure. So this simple construction, no, simple means requires not many long text. It reads us of nasty paradoxes of the set theory. If I had time, I would, it's quite amusing to disprove the basic paradoxes about the set of all sets, or the set which are or are not elements of themselves, and so on. Here all these paradoxes are erased, because here we somehow restrict the possibility to form sets from the beginning. No, in particular, I would say that the S hat is a set, union of all levels in our superstructure, but the set itself does not enter the superstructure. Yes, it's too big. So from the viewpoint of this superstructure, is already not a set in this superstructure. Yeah, and the practice says that for most of our problems, we can stay at some finite level in this superstructure. It's enough for mathematics as it is known today. So we can formulate different things, say Riemann hypothesis, and Riemann hypothesis is also sitting somewhere not very high in this hierarchy. But this is already a model of some restricted set theory which has no these inbuilt paradoxes. Okay, one more comment. This superstructure which I described, in fact, is too large. So here I described two examples of really meaningful and useful objects like group and linear space, which may be put there. But a lot more things there have no meaning whatsoever. Yes, and this reminds me one construction which was entertained by Borges. It is what was called universal library. So it's an interesting thing. So consider an average book, say, of volume about 500 pages. This book, if you count how many letters are there, though it is printed in average font and so on, we can estimate that it contains about 1 million symbols. Yes. No, if it is a special book on mathematics, we can some mathematical symbols. If it's just literature, it's just letters. So about 10 to 6 symbols. Now, the number of possible symbols is within about 100, including letters. No, if you don't like 100, take 1000 if you want to have various fonts there, for example, sizes. Yes, 1000, okay. So if you can put at every place in this book one of 10 to 3 symbols, then the total number of different text of this line, it is, I think, 10 to 3, all to the power 10 to 6. Yeah? No, it is a large number, but not infinite. Yes? So we can imagine that somebody produced this number of books which contain all possible combination of million symbols. Yeah? What does it mean? It is a finite set of books, maybe very large, maybe it's no place in our galaxy for them, but nonetheless it is a finite set of books. And it has the property that every book whatsoever can be found in this library, by definition. Yes? If the book is longer than 500 pages, then we can have multiple volumes of this book. Yes? So any text can be found there. So on one hand, we have a finite object which contains finite collection of text which contains every possible text. Yes? So why not create it and use it? Yes? No, it is in some way obvious that it is a stupid idea, because most of this text will be just random sequences of symbols. Yes? And together with each text, we will have text with all possible mistakes, grammatical and so on. So this means that it is cheaper to compose this text yourself, yes? So it is easier to write yourself all the plays of Shakespeare than to look, to find it in this library. But Borges was himself a librarian, so he felt this more personally. Okay, and so this, what I call model of mathematics, contains, of course, all our mathematics, but it contains much more trash. Yes, absolutely useless and senseless, I would say, information. Yes, and objects. Yes, so we will work with this, I would say, universe, but it does not rid us of duty to find meaningful pieces of it, because taken all together, it is devoid of any sense. Yes, but nonetheless, this as a mathematical object is a great thing, and so we will study it and then extract some meaning of this extension. So what I'm going to do here is to define some great extension of this universe and see what we can do with this. So let's finish today. Thank you. Questions? Okay, next time.